Hello and welcome to today's webinar. This is Mark Plantier of Enercon Industries, and we'd like to thank you for attending today's presentation, What Plasma Treating Actually Does to a Surface to Improve Adhesion. Please note this webinar is being recorded, and you will be able to access both the recording and presentation slides once they are available online, usually within 24 hours. If you have any questions during the webinar, please use the GoToWebinar question tool. You may submit a question at any time during the presentation. We'll reserve time at the end to answer as many questions as we can. For those of you not familiar with Enercon, Enercon is a global supplier of innovative surface treating technologies, including atmospheric plasma and flame surface treaters, which are designed to improve adhesion of inks, adhesives, paints, and coatings. Today's presentation will cover the following topics. We'll look at types of operations that are using plasma and the benefits they are enjoying. We'll examine what plasma actually does to a surface, including cleaning, etching, and functionalizing. We'll touch on adhesion basics, and we'll share insights on plasma and flame technology options. And you'll also, again, have a chance to ask our experts your questions. Today's presenter is Wilson Lee, Enercon's Business Development Director. Wilson has extensive experience in surface treating applications over a wide variety of industries. Wilson works with Enercon customers on developing plasma and flame technology solutions to solve their surface treating challenges. Wilson earned an electrical engineering degree and an MBA from Clemson University. With that, we'll turn it over to Wilson.
All right, thank you, Mark. Appreciate everybody listening in this morning. So let's get started. Who's using plasma? A better question might be who's using surface modification, and that is pretty much every industry on the planet. No matter what you're manufacturing, at some point you're probably cleaning or functionalizing or doing something to the surface so that you can process the next step. This list here is some of the more prominent industries that use plasma or flame in order to achieve their goals. And these would be the adhesives, the printing markets, automotive/aerospace, electrical potting. If you've got an outdoor electrical application, you've probably got a potted electrical circuit, window and door, and wire and cable. All of these, plus basically every other industry, use some sort of surface modification, whether it's primers and chemical etching or just cleaning methods before you prep your part. Okay, so why are we actually using plasma? There's a number of benefits that you're probably seeing. And the reason we're actually having this webinar is we had an internal meeting a few months ago, and this question came up where it was difficult to explain what and why people would use plasma or flame. And so we put this together. But plasma can be used to create stronger bonds. It can reduce material costs. Many times that is in the form of adhesives or coatings or painting. Because you don't need to use quite as much to achieve the same result that you had without plasma or flame treating. You can increase throughput because in most cases, treating or pre-treating a surface with these options is much faster and can be done on a much quicker time scale. You can improve quality. This is by reducing the variability in your process. Many other methods, such as primers and chemical solvents, can be random in nature, and the standard deviation between one part to the next can be very high, whereas plasma and flame is a lot better. And then that leads us to the repeatability, So again, if we're improving our process quality and product quality, we're producing a more repeatable result on each of our surfaces, and that's going to make a better product for you. So what does plasma actually do to your surface? So there's three different things that we talk about: cleaning, etching, and functionalizing. So let's get started. First, let's talk about surface energy. Surface energy of a solid is a complicated subject, and it's not widely understood. If you're on this webinar, you probably understand, or you've heard dyne or surface energy, and those are, or contact angle, and those are just measurements of surface energy. But what does that actually mean? So let's look at this little block down here on the bottom right. Let's assume that is a block of aluminum. And It's just aluminum atoms being held together by their molecules and their bonds. If I decide to cut that block of aluminum, I'm going to start breaking those bonds. Obviously, with a knife or whatever I'm going to use to cut it, I'm not going to actually break the aluminum molecules. So I'm just breaking the bonds between those molecules. If I'm trying to cut a block of aluminum, that's going to take a lot of energy. The more energy it takes to break those bonds, the higher the surface energy of the material is. So metals typically have a higher surface energy than plastics or films, and that's because it takes more energy to break those bonds. Now, if you introduce plasma to a surface, you see the bonding sites there where we're going to start to affect your surface energy. So we're going to be adding functional groups and polar groups to some of those bonding sites in order to increase the surface energy. But again, just keep in mind that the amount of energy it takes for you to break the bonds of any material that you're doing is directly proportional to the average surface energy of where you start. And of course, we want to increase that surface energy to get a better bond or better coating or better painting. So what is plasma? Plasma is basically the fourth state of matter. Physicists will tell us this is the most prominent state of matter in the universe, but plasma is just ionized gas. So when you have a plasma field that's created by, in our case, a high voltage arc, you're going to have free radicals floating around in there. You're going to have negative and positive ions. You're going to have light photons from ultraviolet light. And you're also going to have free electrons bouncing around the surface and bombarding your surface. In nature, you see this quite often. You see it in the northern lights, aurora borealis. You see it in lightning strikes. You see it in electrical arcs. There's a number of places that plasma naturally occurs. But right now we're using, again, a high voltage arc and compressed air generally to create the ions that we're looking for.
Plasma will clean your surface. In this video, you will see plasma attacking contamination on the surface. Static charges are eliminated, so any dust or other materials held on with static are removed. Plasma also removes most organic and some inorganic contamination. As for organics, hydrogen and oxygen ions in the plasma combine with the hydrocarbons of organics to produce carbon dioxide and water vapor. Removing inorganics can be more difficult and usually requires more aggressive treatment or longer cycle times.
Okay, to go back over that, the cleaning effect that we have. There are multiple levels of cleaning that we're going to be doing. The first is removing the static. Anything being held on by the static can be removed. Then you have organic contamination that usually is changed over to CO2 and water vapor. And then you have inorganic. So those are the three things that we're going to be cleaning. The inorganic by far is the toughest, and depending on the level of inorganic contamination, you may or may not be able to use certain surface cleaning techniques, including plasma. So that sometimes will limit what you can do. But in most cases, we can get most of those contaminations off of the surface.
Plasma will etch your surface. There are many ways to increase the surface area for improving bonding: laser ablation, sanding, sandblasting. In this clip, you will see that the plasma can etch your surface by changing the smooth manufactured surface into the surface you see on the right. This increases the usable bonding surface area and improves overall bond strength.
All right, so then after the cleaning step, or basically at the same time that the cleaning step is taking place, we're also etching the surface. This is the manufactured surface that you're looking at in the bottom right-hand corner, but there are also natural surfaces that we treat from time to time, and you get a completely different look to that surface. It's much more jagged if you were to look at it under an electron microscope. But basically what happens then is you do the same thing. You are eliminating some of those peaks and valleys, and you would think that those peaks and valleys would actually increase the surface area, and they do. The problem is you're looking at it at such a small level that the adhesive or the paint or the bond can't actually get down to the surface. So whether you're looking at a manufactured surface or a natural surface, this etching effect increases the overall usable surface area.
Plasma functionalizes your surface. Functionalization, sometimes called activation, means that you are adding hydroxyl or carboxyl groups to the outermost molecular layers of your surface. In this video, you see the ionized gas bombarding the surface. Oxygen groups, OH groups, and hydrogen groups attach to the surface, increasing the surface energy. By adding these polar groups, you increase the overall surface energy and the ability for inks, coatings, and adhesives to improve their bond to the modified surface.
Now we're looking at probably the most complicated of the effects that plasma or flame has on the surface, and that is adding the polar groups that were discussed in that video. You're adding these on a molecular level. You're changing the outermost molecular level of your surface, and it is adding polar groups. When you increase the surface energy and you do a dyeing test on it, it's that polar energy that you're increasing. And the polar groups in that case are allowing you to have a better bond. Someone described it to me once as a Velcro on the surface, for lack of a visualizing term there. So you're actually putting those polar groups, and that is what gives you a more effective bond. And depending on the type of treatment that you're using, for plasma, it is hydrocarbons that you're putting on the surface, or not hydrocarbons, it is functional groups that are, and I've lost my train of thought, apologize for that. With flame, it is carboxyl groups, and with plasma, it is hydroxyl groups. Each one of those does slightly different things to the surface, but they do have the same effect. And again, increasing the surface energy is what we're looking for here. Now, this is an animation of what is happening with the plasma stream as it hits your surface. The little lines there are representing the plasma as it comes down, or maybe the flame as it's coming down. And then you have those same groups we discussed earlier. You have hydroxyl groups, you have O2 groups, you have negative and positive ions. You also have free radicals that are bombarding the surface. And then you can see they're starting to attach themselves to the molecular layer of the surface. And that's what we mean by adding functional groups to that surface. Now, this is a molecular chain, the outermost molecular chain of a hydrocarbon in this case. And we're seeing what happens when you start to treat it with plasma. This is prior to plasma treatment. You see that there's one functional group, one OH group over there on the surface, but most of the other are nonpolar groups on that surface, and you're not going to have a very good bond to that. But after treatment, with the next slide, you'll see that you're starting to add more OH groups, O2 groups, and these are the polar groups that you're adding, again, on the molecular level to the outermost one or two molecular chains in that material, and you are going to increase the surface energy of this part. So, how long does the treatment last? This is probably the most common question. So we've got a little graph here that's going to show us what happens when you treat something with either plasma or flame. In this case, we're going to use dyeing level because dyeing is directly proportional to surface energy. So an increase in dyeing level is an increase in surface energy and an increase in bonding. So you've treated the surface. You start, in this case, we're looking at maybe 10 or 20 dyne, and it immediately increases up, in this case, to over 60 dyne. So we've gotten a good treatment. Well, how long does it last? Well, that's based on a number of questions. First, it's going to steady state for a time t. Now, t is going to depend mostly on the material and the method in which you treat it. For plastic, sometimes you may have 4 to 24 hours. For some metals, you may have 18 to 48 hours. I've had some carbon fibers that have lasted for weeks. So time t just varies on the surface, and you have to basically run this test to figure out what that is. Then after that time t, you're going to start seeing a degrading effect over time. Now, generally, you never get back to the surface energy level at which you started. In this case, again, about 10 dyne. We're going to steady state here at maybe 35 dyne. And the reason is that is because you have changed that outermost molecular layer. You've added functional groups to that surface that are not going away. And so that is why you have, in effect, increased the surface energy. So how long does it last? I have T1 out there. So let's say that I have done some tests and I need to be above 40 dyne in order to get a good bond for my surface. In this case, I need to figure out what T1 is. So I get up to 60 something, and I've run the trials, and I know that above 40 I get good bond or I get good adhesion. So that's what T1 is. And again, that's going to vary for every material. Let's say that I only needed to be above 30 dyne in this particular model to get good adhesion. Well, then basically my treatment now is permanent because I've started at a lower dyne and it's never going to get back to 30 in this example. So the treatment will last as long as the material will stay active, but as long as the material stays active above the level with which you need to get that good bond. And again, you can only figure this out with a trial and running a survey for your material, because every material is slightly different. Every treatment is going to be slightly different. It would be nice to have a database that would tell us all this, but in the end, it's going to come down to probably a test. So now let's go over some adhesion basics. On the left, you see a drop of water on the surface of a material. You have two different forces attaching themselves, or in play, I should say here. Cohesive forces are the forces between the water molecules, and the adhesion forces are the forces between the water and the surface in this case. When you wax your car, you're going to increase the cohesion. You're not going to increase the cohesion, but you're going to decrease the adhesion forces in that. So the water beads up, as with the untreated sample over there on the right. The water beads up and rolls off. If you rain extra windshield, you're going to decrease that adhesion bond. So again, your water is going to bead up and roll off. With our methods, with plasma and with flame, you are going to increase that adhesive bond. You're increasing those polar groups, you're increasing that surface energy, and you're going to see the water wet out as it does there on the left side of the other picture. So these are the forces that are in play, and these are what affect your surface energy and whether or not you're going to get a good coating, whether or not you're going to get good adhesion or good printing. It's also interesting to note that you can tell the difference in the height of the treated surface versus the untreated surface. And by that I mean the amount of material it would take. You can easily see that on the right, I would have to completely cover that surface with adhesive in this case, and my level there would be much higher than the treated surface where I'm getting good wettability. What that basically means is if I'm using adhesive in this situation, I'm using more adhesive. And generally speaking, when we test materials and we try to figure out when they're going to break, what we're looking for is a cohesive failure. And that basically means that you've got adhesive, after you've broken the part, you've got adhesive on both sides. So whatever you're bonding to, you're going to see adhesive on that side and what you've pulled it off of. So a cohesive failure basically means that you are straining the limits of that adhesive. So if I have less adhesive there to break, I'm going to have a stronger bond. So basically, in this case, you can see that you can use less adhesive and get a stronger bond by having the properly prepped surface. So what are some impediments to adhesion? Here you have a low energy surface, and this again is something that we would like to try to remove. So what causes that? Well, surface contamination. We've discussed earlier how we can remove materials that are on the surface, whether they're organic or inorganic contamination or things being held on by static. Another problem we run into is migrating additives. If you're putting flame retardants or some other additive into, say, your plastics, those can be limiting factors to adhesion. Recently, I heard that there's some changes in the plastics being used for wire and cable because of some larger delta T or delta temperature that these wire and cables are seeing when they're on ships heading around the country and around the world. So they're having to add more additives to this, and this is changing the profile of their material and their surface. All of these give you the limiting bonding sites and makes a very hydrophobic surface. So selecting the right plasma technology for your application.
All right, we're going to play another video here. It'll show the Enercon's blown ion and flame systems in operation. There is no audio for this portion. This is just a video.
Okay, so in that video, real quickly before we get started with this, we saw the blown ion 125, which was the smaller plasma stream that you saw there, treating terminal blocks for printing. The second was the blown ion 500, which is our larger 2-inch multi-port design, and that was in a window and door application. And then you saw flame treating a dashboard. Each of those are different applications. They require different cycle times, and so that's how we go about trying to figure out what application is best for you. Now, we have another that was not shown in that video. We have a blown arc, which is similar to a blown corona. The treatment head is about 2 to 3.5 inches wide, so it's about the area that you're going to get treated. It can only be used on non-conductive parts, so this is mostly for plastics, and it's ideal for a wide range of applications. Generally speaking, we use it for labeling applications and things such as that, or maybe even printing applications when you only have to bump the dyne level of the surface energy up a little bit. You're not going to get quite the intense nature that you would get from a flame or a plasma with the blown arc. But again, if you're starting at 30 or 40 dyne and you only need to go to 45 to 50 dyne to get a good treatment, this may be a good option. And again, it covers a much larger area than just a regular plasma. The blown ion treats about 3/8 of an inch to a 1/2 inch. You usually are treating at a relatively close distance from 1/4 of an inch to 3/4 of an inch, depending on material. You can treat all types of material, conductive or non-conductive materials, and it is used in a lot of different applications if you need to get down into smaller areas. Generally, you can put this right in front of an adhesive dispenser if you're doing a bonding application. Or you can put it on some sort of robot to get all the areas that you need. But generally, it is for a spot treatment or a line type treatment, and we can go from a 1/2 inch to putting multiple heads together to treat whatever width that you need. It's also a very high speed application. Now, the blown ion 500 multiport, which is what you see here, treats up to 2-inch at the same intensity as the blown ion 125 that we just saw. This gives us the ability to treat much wider areas, much faster, and in much faster line speeds. The other alternative, generally, when you're talking about plasma, is some sort of method of moving or rotating the head around an axis so that you can get wider treatment areas. This may be very good for some thin films and things that are thermally damaged. But if you're trying to treat metals or you're trying to treat some larger plastic parts, you're not going to get the same level of activation. You're just not, the ion density is how we refer to it, and that's just the amount of ions hitting one area at one time is much greater with the blown ion 500 than it would be with any sort of rotary sight system. And we also have flames. And this is going back to when I got confused a little bit earlier and got tongue-tied. I apologize again. These are adding carboxyl groups to the surface instead of the hydroxyl groups. Many times on many surfaces, they'll act exactly the same. Going back to that dash application, you can use blown ion plasma on a dashboard and it works just fine. Flame in this case is just a little more forgiving. We can throw the flame a little bit further so we don't have to be quite as precise on the distance to the part. And we can make a flame head virtually as big as you'd like. So if we're trying to cover large, wider distances in a shorter cycle time, flame tends to be the best way to go.
With that, we'll get to your questions. We've got a few here already. Wilson, the first question is functionalization activation easily contaminated by touching the surface?
Yes, it is. When you activate a surface or functionalize a surface, you're basically making a surface that is very, very easy to stick to. So anything that you touch it, or anytime it comes into contact with anything else, if you're in a relatively dirty environment, it's going to attract things from the air. So yeah, you are increasing its ability to attract to basically anything, including paints and coatings and adhesives. So yeah, we usually recommend that you treat right prior to whatever that next step is going to be, so that you don't have to worry about other contaminations getting onto that surface.
Are there instances where plasma treatment does not help adhesion? How do you optimize plasma treatment?
Unfortunately, there's always instances where plasma does not work. There are certain materials, fluoropolymers come to mind, that plasma is not very effective on, at least open air plasma, which is what we're talking about here, or flame does not work on. So there are limits to that. Other issues sometimes are just, again, cycle times and how quickly and how large the area is which needs to be treated. In a roll-to-roll application, it can become quite economically costly to treat, say, a 1 meter wide aluminum or stainless steel application. It can be done, but again, the economics of it make it a little more difficult. So there are limitations. The best advice I can give is just to contact Intercon, and we can put you in touch with the right person, or even myself, and we'll be happy to walk through your application and try to figure out what might be the best solution for you.
Here's a question regarding how is the plasma created, and can the energy level be controlled?
In our blown ion systems, the plasma is created by passing compressed air over a high voltage arc, and that creates the ions. In theory and in practice, actually, you can control that power electronically that's coming out of the jet. In practice, however, it's generally just easier to control the distance and the speed. You just keep the variables that we're interested in usually are distance and speed, and then the power level of the plasma. Since we can hold the power level constant, then all we need to do to change the treatment level is either move further away from the surface, move closer to the surface. In that case, if you move closer, you're going to increase the intensity of the plasma. If you move further away, you're going to decrease the intensity of the plasma. Or you can just change the speed at which you're treating. So a slower speed would increase the ion density and increase the surface energy. A higher speed would decrease the ion density and the surface energy. So yes, these things can be controlled through the system, but it's significantly easier to do in your process.
Wilson, what are any safety issues or concerns when using plasma?
With plasma, the main safety issue is just the temperature. The plasma itself, as it comes out, is roughly 120 to 130 C. So it is very hot. The plasma nozzle gets hot as well during activation, during its use. So you would want to use any sort of barrier that you would have to keep hands away from that. Most of the time you're doing this with robotics as well. So generally speaking, there is already robotics safety measures in place so that a worker cannot get to that robot. So sometimes it is very, very easy to do that, but we do offer shielding and other methods so that, again, workers cannot get close to that plasma and touch it. But heat is the main danger.
One person has a question. In the videos that we showed, the blown ion nozzles are basically perpendicular to the surface being treated. Are there any situations where having the nozzles at other angles are beneficial?
Yes, there is. If you change the angle of the approach, you can effectively increase the area which you're treating. Now, you have to be careful there. If I'm perpendicular to the surface and I'm only a quarter of an inch away, I'm going to get one ion density. And so I'm going to increase the surface energy to a certain level. If I change that to a 45-degree inclination to the surface, at the point where the plasma first meets the surface, you're going to be getting a higher surface energy than you are, say, a half an inch down that material. So again, you need to run a test to see what level is getting you the bond that you need. So again, if I need to get it 55 dyne, I want to make sure that I get that whole area that I'm treating to 55 dyne. And you're going to get decreasing levels of surface energy increases the further away you go from that nozzle. So yes, you can treat it at an angle. We have some nozzles that treat specifically at an angle on purpose for a lot of window and door applications. Again, you can do it. You just need to run the test to make sure that you're getting to the right surface energy level, I should say.
Someone would like to know what techniques are there to measure surface free energy of a treated surface?
The two most common are dyne and contact angle. Dyne is either in the form of a solution, or you can calculate dyne using a device such as a Cruce device, which is going to take a couple of different measurements on that surface with a couple of different liquids, and then you can calculate what the surface free energy is. You can also use a goniometer, which is a lab version of a Cruce device. There's also other handheld devices from Brighton Technologies that you can use to determine contact angle. Those are the best ways. One thing to keep in mind is dyne level is proportional to surface energy. Contact angle is inversely proportional. So a low contact angle is a high surface energy. So those are the two most common methods. There are other methods to look at the cleanliness of a surface that will also help you figure out the surface energy. You can also do FTIR scans to make sure you're removing all the things that you want off of the surface. But again, dyne and contact angle are the most popular.
What is the difference between corona treatment and plasma treatment?
I don't know. I'm just kidding. Corona is a much more short-term. It's difficult to describe, but I usually talk about it in such a way that what is the effect on the surface. If I'm using corona, I'm usually using that on a wider surface, generally a roll-to-roll application, and I'm going to get a very short-term increase in the surface energy. So that's why, again, it's used in an immediate roll-to-roll application where you've got maybe a corona arm or a corona bar treating a film before it gets printed, or treating a film before it gets laminated. It's doing a lot of the same things. It's going to remove some static. It is going to do a little bit of cleaning to the surface, but not the same level of cleaning as flame or plasma does. And again, it is very, very time sensitive. So generally speaking, a corona treatment does not last as long as a plasma. Plasma, on the other hand, again, is just ionized gas. You're creating a plasma also when you use a flame treatment on that surface. You're still getting the ionized portion of that onto that surface. You're doing a lot more changing, I should say, of the outermost molecular layer when you use plasma. And so those treatments tend to be longer lasting and will increase the surface energy to a greater extent. Again, all of these are generalizations, but corona is more of a activation of the air around a film that you do when you're, again, in a roll-to-roll application. Now, there are some larger applications. We have a tangential treater that you can pass over some wider areas that you can get some activation with. That will be a little more complicated. So again, the best bet is just to reach out for one of us and let us walk through your application and try to figure out if it's a better corona application or a better plasma application.
Wilson, someone would like to know, do you have any suggestions for treating stainless steel?
Plasma works very well in stainless steel. I've done a number of applications with that. It's already got a relatively high surface energy to begin with, but if you are treating stainless steel, you can increase it to an even higher level. You can also do some cleaning of stainless. A specific application that we haven't discussed yet would be critical welding applications for stainless and for titanium and for aluminum for that matter. But if you have a critical welding application, we've got a number of customers that use open air plasma, what we call the blown ion, and to treat that surface and to remove as many inorganics and organics from the surface as you can. And the more of those that you remove from that surface, the better that weld is going to be. So yeah, stainless steel, going back to your original question, treats very well, and you can get some cleaning effects there on the surface as well.
All right, we've got a couple of questions related to how long treatment lasts. How long does the functionalization effect usually last after treating a surface? What is the explanation for the decrease in surface energy after treatment? And can you speak about a general amount of time plasma activated glass would last?
Glass we'll start with the last part first. Glass is pretty stable. We've done a number of windshield applications and treating of different types of glass that goes onto displays and things such as that. So glass is very stable. It generally lasts, I would say, between 12 and 24 hours. And so you can get pretty good functionalization of glass, maybe even longer than that. Maybe you can even go to 48 hours on that. So it's possible for us to treat something in the lab with glass. As long as we wrap it properly, it goes back to your lab and in a very good condition, so you could do some bonding or printing on it. The reason that the treatment is degrading is, again, first off, there are things that are happening on the surface that are not permanent. And so some of those ions where you're creating those polar groups are permanent. Other materials or other of those functional groups that are going onto that surface are not permanent and will degrade over time. Also, you're creating a highly active surface that wants to attract itself to other things. So there are impurities in the air that are going to attract itself to the surface. And again, you're going to put that on there and it's going to decrease the surface energy. When we treat something in the lab, we generally wrap it in either craft paper or aluminum foil, and then we put it in some sort of bag. If it's a critical application, you might store it in a forensics type bag. Those are very clean environments. When you do roll-to-roll applications and you treat something and then you roll it back up, you'll generally find that the surface energy is preserved until you unroll it. So that suggests that, again, it's the atmospheric things going on around your part that are creating the surface energy over time.
All right, we're going to continue to try to get to as many questions as we can. You can also call or email Wilson at the address and phone number on your screen. Next question deals with that many of our systems seem geared towards non-conductive substrates. Is that because of arcing concerns? Which systems can be used with conductive substrates?
Well, the only system we have that you can not use on a conductive surface is Corona and a blown arc. Blown ion 125, blown ion 500, and flame can all be used on conductive surfaces. What was the second part of that question? I apologize.
No, that was it. What systems could be used for conductive? Okay. Is there a risk of arcing?
There is not a risk for arcing with most of our systems, and the reason is we have built in a safety measure in the way we produce our nozzle so that you're not going to arc to the surface. So if you're looking at a circuit board, you can treat it with our normal either blown ion 500 or blown ion 125 nozzle, and you should not arc to the surface. The reason for that is the arc is contained inside the nozzle. Now, we do have nozzles where the arc is exposed on the end. That is for generally metal applications, and there is a little bit of a risk there of arcing to the surface. Now, when something does arc to the surface and you're using conductive material, it's just best to ground that in some way, shape, or form. I would not say it's overly dangerous. We're talking about milliamps that are being transferred to the surface when you're talking, again, with plasma. But it would be a safety feature that we would add, ground, excuse me, put a brush onto, if you're doing some sort of, roll-to-roll type of application and it's metal, you might want to put some brushes on there that are grounded. You could, if it's a part that is steel, copper, or anything that's conductive, you might want to ground the area around it so that you don't have an issue there. But the electrical arc that sometimes goes to the surface of those materials does some interesting things to the oxide groups, and in many cases, they can be beneficial to the bonding or the cleaning that you're trying to do. So I wouldn't be concerned about it, but just be aware of it. And again, we can discuss your specific application and try to come up with the best way to do that. But in general, we're not going to ground to the surface.
Can the plasma process damage sensitive parts like electrical circuits or electrical cables?
Electrical circuits and electrical cables, again, no, not if we're using the right nozzles. There's no potential there for it to ground to that surface, so you're not going to damage that at all. So we do a lot of electrical potting applications where, again, you're an outdoor application and you need to pot that circuit so that it doesn't get wet. You can treat that at virtually any distance and you're not going to arc to that surface. As long as you're using the right nozzle, you should be fine.
Would plasma treating a surface multiple times degrade the substrate, thinking in terms of glass or polycarbonate in particular?
some materials you can overtreat. In some materials you cannot. Glass treats pretty well. I've never seen a degrading of the surface of glass. But again, the only way I can think of is if there was a coating on the glass maybe, and you got the temperature up too high, that you could start to damage the coating that's on the glass. Polycarbonate is a very interesting material. It doesn't treat particularly well with plasma, with open air plasma or blown ion plasma. It treats better in a low pressure chamber. It also has a shorter term activation. You can treat it with an open air system like a blown ion or a flame, but you have to be moving pretty fast, and you may have to treat it multiple times just because it doesn't take to the treatment quite as well as other materials.
All right. Next question is, are there any restrictions or materials that in the plastic family that are not susceptible to responding to the plasma treatment?
The most common is, as we mentioned earlier, is fluoropolymers. So anything with fluorine like a PTFE, a PFA, if it has fluorine in it, it typically does not treat very well. It's just a nature of what happens with the fluorine atoms once you treat it, and the way that they migrate through even a solid surface. You'll be treating that surface, and a few seconds later, the surface that you treated is no longer the surface of the material. So fluorine doesn't work very well. There are other materials that just don't treat as well. Some of the thermoform materials that you use are less susceptible to treatment with plasma, but again, sometimes flame works very well on those. So you just have to, again, many times we just have to test it, because even if we're able to increase the surface energy, we may not be able to keep it raised to a point or to a length of time for your next step. So again, a lot of times batching applications are out, but many times we can. So you just have to, it's an unsatisfying answer, and I realize that, but many times you just have to run the test on your material. Another material that doesn't treat very well is POM, and again, that's a POM, which is used in a lot of thermoform molding applications, and it's just one of those materials that's difficult to bond to. So give us a call. We'll be glad to discuss your specific application, and if we don't know anything about it, we have a lab in Milwaukee, or Menominee Falls, I should say, and we can send your materials there and see how they are affected by the different treatment methods that we have, and we can recommend what might be best for your application.
All right. Understanding that it's always best to perform the next process on the treated surface as soon as possible, this person has a situation where they need to wait to coat after surface activation. What's the best way to handle and store the substrate to ensure the surface does not become contaminated?
The cleaner the environment, the better. And again, if you can store it or put it in some sort of, you could put it in a gaseous area with like an argon gas that is if you could store it in that type of environment, you could prolong the surface energy. You could wrap it again. Like I said, we use craft paper and aluminum foil. I would not store it in things like Ziploc bags. They have a coating on the inside that will affect your surface. You can use those again if you wrap it with something else. So again, just the cleanest environment possible. Just know that you're creating an active surface that things in the air are going to want to attract itself to and stick to. So the best bet is to do that in the cleanest room possible. But if that's not possible, again, going back to the graph that we had earlier, again, if we run a test, you may be at a point where once you treat the surface, it does not usually get back to the same level of activation as when it started. So you may have an application, and we've had a few of them, where you can treat it and the application is basically permanent because you don't need to be a little bit of a bump in surface energy to get it above a level where you can print on it or coat with it.
What would be best for a carbon epoxy composite surface? What technology?
I would probably recommend plasma. It generally works better on those types of surfaces. Flame will do it as well, but plasma, carbon composites, and things like that have really worked well in the past with either the blown ion 500 plasma or the blown ion 125 plasma.
Can you talk a little bit about the difference between air plasma and vacuum plasma?
Vacuum plasma is a batch application, sometimes called low pressure. It is done in a chamber, so you can find low pressure chambers all over the place. You can go to YouTube and they'll show you how to make a pressure chamber out of a microwave. But the problem is you have to be able to control the gases that are going through there. So what you basically do, if you're putting something that's a very random 3D part that might be difficult to treat with atmospheric, you could put that part into a vacuum chamber. You take it down to, say, 10 millitorr, almost a full vacuum, and then you you turn on the electrodes that are in there, and you introduce a process gas that's going to give you the desired effect onto that surface. In general, you can do everything with outside of a chamber that you can do inside of a chamber, but many times it's just not practical. So you see a lot of, if it's something that is a batch application, it can be used as a batch application. I'm thinking of medical tubes and medical filters and things like that, many times that batch application is just fine. You can go to the vacuum chamber, but if you're in an inline process, it's just very difficult to use batching applications that you have to do with the vacuum system.
Here's a question on what's the typical range in dynes during production from part to part? I think the idea being if they're measuring dynes on parts that go through the same process, what type of variability should they see?
You're going to see very little variability through the process, again, as long as you're maintaining speed and the correct distance from the part. The variability many times will be in the raw material coming in. So depending on if you use multiple suppliers, or just depending on one batch to the next of a part that you use every day, the incoming dyne level or contact angle may be different on those, and that may be significant. It may be 4 or 5 degrees contact angle or 4 or 5 points in a dyne, and what we're doing is going to increase that surface energy by a factor of what we call the delta. So we might only increase it by 20 points dyne or 30, reduce it by 30 degrees contact angle. So if we started at a higher level, we may not be able to get down to quite the same level. So making sure that the material that comes in is as consistent as possible is one of the best ways to make sure that you're getting good, consistent treatment after the plasma. Now, that's not always the case. Many times there is a limit to what plasma can and can't do as far as how much it's going to treat that surface energy. You may, again, glass is a good example. Glass is very easy to treat. If you're using contact angle, you can almost get complete wettability after just a minimal amount of treatment. And so you don't have to increase that speed or decrease that speed to change that very well. You're going to almost immediately activate the glass to a very, very high level. Other materials are not as fortunate. Some take a very specific amount of energy to get it up to that high level, and variability in the material coming in can affect what happens on the other side of the plasma treating.
Will materials that contain such things as plasticizers tend to delaminate from their coating over time, even if the surface has been plasma treated, or does the surface stay stuck once it's been treated?
Unless something is getting to that bond from another method, you're usually good after the bond has taken place. Where that turns out to be a problem is salt sprays and things like that with metals. Sometimes you can get things creeping in through one of the materials that are going to affect the bond. But if nothing is attacking that bond from inside the other materials or from an edge, generally speaking, once you bond it, you're good. But again, there's instances where after you bond something, that certain materials can get into that bond and start to eat away at the adhesive. Generally, it's not really affecting the surface, but it can affect that adhesive and reduce your bond strength.
Okay, we have someone that's trying to print UV cured ink on polyethylene. They're thinking of adding a small amount of filler to enhance wet out. Adding the filler would be coated with PE. Wondering if the plasma treatment would expose the filler and thereby increase adhesion and wet out.
It should increase the adhesion and wet out. Again, we would need to know more about the coating and what you're doing, but I would think in general that's a pretty easy application.
Okay. What are limitations on mechanical roughening? Is it limited to plastics, or can metals also have a surface roughened as well?
Yes, not to the same extent for obvious reasons, but yeah, every surface has a little bit of roughening to it. And you can, again, increase the intensity by slowing down or decreasing the distance to the surface. So we are doing a number of applications now where we are cleaning metals, and in order to clean metals, you have to get down to, you have to do a little bit of roughening there. And there's also other processes that we can do in conjunction with plasma that will also improve that as well. So there are multiple things we can do with metals to get, again, contaminants off the surface and to roughen that surface at the same time.
All right. We'll get to, I think, one more question here, and then if we did not have time to get to your question, we can follow up with you after the webinar, as well as you can reach out to Wilson directly. And the last question is, what tends to be more effective, blown arc or blown ion?
I wouldn't say that one's more effective than the other. I would just say they have different applications. If I'm trying to put a label onto a plastic, a blown arc is probably going to be the easiest way to do it. You can treat a larger area. You can do it at a relatively high speed, and economically, it may be the best way to go. If I'm trying to put an adhesive or bond two things together with an adhesive line, then blown ion may be the way to go. If I've got to print on a surface, sometimes a blown arc might leave a trail on that surface, as you can see visually, that you may not want if you're just printing on it. So one's not more effective than the other. They just have different applications with which is more dependable or more accurate or more suitable for that application. So again, for the application, they'll both work. For individual applications, one might be better than the other, but they're both very dependable.
All right, thank you, Wilson. I'd like to thank our audience today. Some really great questions here at the end. Again, feel free to reach out to Enercon if you have any follow-up questions. And if you have any ideas for future webinars, please send those to us as well. This will end the webinar for today.